Well, we're going to have some upsolving, and the problem for upsolving is from today's contest. Today was AtCoder regular contest 175, and there was a task E, which I was trying to solve, but in vain. We need to divide a cube with a side length of n into n cubed smaller cubes, such that on each of three faces, if you look at them normally, perpendicularly, you'll see the same picture of k cubes. That is, they should not overlap, for example. Okay. So the set of all xy's should be equal to the set of all y's z's, and should be equal to the set of all z's x's. Actually, there are two main ways to achieve this. Yeah, first obvious one is to take a point with coordinates x, x, x. If you take it, then it indeed has the same impact on all three sets. However, there are more to that. For example, you can take x, y, z, where at least two of these three elements are different. So they might be either all three different, or two equal and one different from them. And you can take these 3 points, x, y, z, y, z, x, and z, x, y. If you take all such triples, all three, yeah, then actually in all three projections you get xy, yz, and zx. For example, in these coordinates here you have xy, yz, zx. In these coordinates you also have yz, zx, and xy, etc. So you can add 1 to your set, and you can add 3 to your set. The question is, can you get everything? Well, you can get nothing if you don't take any cubes. Also, you can take all possible cubes and squared. I'll explain later how you can do it. I will explain it now, actually. So this is an idea which I managed to think of during the contest, but I thought that it's not productive, and I was wrong. It was productive. So x plus y plus z equals 0. Let's consider all such triples. Notice that for each pair of fixed x and y, there is exactly one z, which complements this pair to 0. So if you just take all these points, they work in that way that all three projections are equal, and they are equal to the whole plane, to the whole square. Now we need to analyze this set, yeah, because we are given some number from 0 to n squared. Yeah, if it is exactly n squared, then we are lucky, but sometimes it is not n squared exactly. This means that we need to remove some numbers. Okay? So actually, you can see that this set can be represented as several such triples and several such triples. Several such triples and several such triples. Each time you remove this one, and the majority of the triples are of this type, you get -3, but you can also remove this triple and get -1. Okay. So you can get either -3 or -3 or -1. Well, let's explore it. So first of all, if n is divisible by 3. If n is divisible by 3, then actually the number of such triples is just n, because not n but 3, yeah, because there are triples 0, 0, 0, n over 3, n over 3, and n over 3, and 2n over 3, 2n over 3, and 2n over 3. There are 3 such triples, and the rest of the triples are split into triples. So you can take any number of such triples, and then if you get a wrong residue, you can complement them with these 3. So that's kinda easy. But it's not the end of the problem, of course, because there are also 1 modulo 3 and 2 modulo 3. Okay? So in these cases, we need to think of some other construction, some new construction. So first of all, in each of these cases, you also have a triple 0, 0, 0. And that is the only triple with equal numbers. So the only triple in which all 3 numbers are equal is 0, 0, 0. Okay? That means modulo n, of course, here. Yeah. So you can get any number which is 1 modulo, for example, here, yeah? You can get anything which is 1 modulo 3. Okay, and 0 modulo 3. But there are questions about how to get 2 modulo 3. Yeah, and in this case, there are also issues, because in this case, you can get 2 modulo 3. What can you get actually? I see. Also 1 and 0. Why I thought 2 modulo 3? Because n is 2 modulo 3. But actually, the number of the total number of triples is not n modulo 3, it's n squared, and n squared is also 1 modulo 3. So in this construction you still get 0 or 1. So we can get 0 or 1, and the only question is, can we get 2 modulo 3? Yeah, so we need some number of cubes, 2 modulo 3, which can be divided into such triples into such triples into such triples. Okay. This shouldn't be hard. We just need to think about it. Okay, what can we do? What can we try to do? We can try what can we try? For instance, let's consider something like AAB. For example, we can consider 1, 1, n minus 2, I think. Let's try and do it. So we consider a1, 1, n minus 2. It lies in the following triple: 1, 1, n minus 2, 1, n minus 2, 1, n minus 2, 1, 1. Now let's remove all 3 of them and instead put just 1, 1, 1. So it will be the only exception. So initially we have all triples, so we have k squared n squared, which is 1 modulo 3. Now we removed 3 triples and added 1 triple, so now it becomes 1 minus 2, which is 2 modulo 3. And then we can remove as many triples as we want, so we can actually get any number modulo 3. Okay? So that should make sense. Now we need to implement it and get accepted. I will start from reading the input, of course. Okay, after reading the input, I will need solve tests. It is just a thing to have a multi-test. Yeah, so in the testing system it will be just t equals 1, but for me it will be t equals 1 and 9. Okay, now void solve bool solve test. And here we only need to read n and k. We need to take PII. Okay, actually, let's make a structure. Triple, which consists of three numbers. So during the solve test, we will need to make vector of triples. And we need to output it. Also, if we failed to read it, we need to return false. And here we will need to return true. Also, we need a vector for triple we need to write all the numbers. Okay, so we only need to find ours, which is vector of triples. Nice. How do we do it? So firstly, like we have some basic solution. Yeah, so what is the basic solution? Basic solution is among these triples, take the needed number modulo 3. Next, if we need to have 2 modulo 3 but we can't, we take this triple and ignore these pairs. And finally, we just add 3 if we can. I think that's it, actually. Yeah, so okay, let's make the most basic solution. So we have vector triple ans. Yeah, and so the condition to stop is simply ans.size is equal to k. Okay. So we have numbers I and j. We need to understand, do we need what do we need to do? Yeah, so basically so when do we take 0, 0, 0? Okay, let's first calculate the third number. Int L equals, how can I calculate it? It's like 2 times n minus I minus j, and while L is at least n, L minus equals n. So this is our number, L. So if they are all equal, Okay, fine. Actually, let me say that an important thing. So if k equals 0, it will be convenient for us to just return ans. Why is that? Because I actually I always want to take 0, 0, 0. So if I equals j and j equals L, then it is either 0, 0, 0 or n over 3, n over 3, n over 3, or 2n over 3, 2n over 3, 2n over 3. Okay. So, first things first. If let's make some bool easy. It says that n times n minus k percent 3 is 0. Yeah, so k is equivalent to n squared modulo 3. So if it's easy, we just take all such triples. ans dot pushback ijl. Which cases are there also? Also, there is a case when so we have 0, 0, 0. Okay, it's easy to explain when do we take 0, 0, 0. We take 0, 0, 0 in two situations. Either when we have 3 divides n, and we always take 0, 0, 0. Actually, if n percent 3 is 0, what do? We need to take it. If I divided by n divided by 3, yeah, so it is either 0, 1, or 2. When do we need to take it? Oh my god. Okay, I think we need to categorize it and classify it on paper, and after that we can write a solution. So let's simplify it as much as possible. So first of all, two first numbers are equal. When do we take it? First of all, just any triple. If a triple consists of 3 different numbers, we can always take it except of 3 different numbers, or maybe 2 equal and 1 different. We always take it if we need plus 3. There is only one exception. We don't want these triples. Sometimes we don't want these triples. Also, there is a problem that that I don't want to take the same triple a lot of times. How to prevent us from taking the same triple multiple times? For example, we can avoid that. Okay, this is becoming really strange. Okay, I see what I need to do. Okay, this is a bit redundant, but let's make a vector bool taken, which says that we have already taken such a pair. Okay, so first of all, if ij is already taken, then continue. So that's it. Via this method, we will skip triples if we don't need them. Okay, if we have a triple, also let's write a function take. Auto take int a int. Actually, let's have triple t. How to take a triple? To take a triple, so we always need to take it. How to take one triple? Okay, to take one triple, you just need to say that taken t0, t1, t2, t0, t1, t dot a is false, it's true, and dot pushback t. How to take not one but whole triple? Not only do we need to take t, but also if t dot a0 is not equal to t a1, or t a0 is not equal to ta2, so if there is some difference, then we also need to take their cyclic shifts. So we say take one of ta1, ta2, ta0, and take this one. Okay, we can now take a triple. So in the only case in which we don't want to take this triple is this one. Sorry. So what do we write? We write bool hard equals, so n%3 is not 0 and k%3 is 2. This is a hard case. So if numbers are different, let's calculate the number of ones. If ones is true, this means that we have this strange case. And in this case, we need to skip if we have two ones, then we also have to ignore n and n minus 2. We need to ignore n minus 2. So how do we do it? If I is not 1 or j is not 1, then continue. So I only want to look at this triple when I get two ones. Now, if we have... Okay, let's also make a thing called want, which says, do we want a triple? And it's kind of easy. It simply says that ans.size plus 3 is still at most key. This means that we want a new triple. Okay, I don't want this. So I have two ones. In this case, I need to ignore it if I have a hard case. Yeah, so if hard, then I need to take triple 1 1 1. So if we want, we take else we just take one. And here we also take IJL. Okay, what next? Actually next we want to consider the other case, and the other case is simply that all numbers are equal. We always take 0, 0, 0. Do we always take 0, 0, 0? When do we want to take 0, 0, 0? Let's again do it on paper. So if 3 divides n, we want to take 0, 0, 0 always. And if 3 does not divide n, if we want to take 0, 0, 0, when k is 1 modulo 3 or 2 modulo 3. So if it is 0, then we take either if n is divisible by 3 or if k is not 0 modulo 3. Okay, otherwise we have two more cases. I is n over 3. So when do we take n over 3, n over 3, n over 3? We take it when it is divisible and when it is 1. Oh no, when it is 2. 0, sorry, 0 or 2. Else we need to take only for 0. Then let's assert that ans with size equals k and return ans. Okay, let's try it. Okay, debug assertion failed. But not because of us? Ah. We'll have to be more careful. Okay. Actually, does it mean that the assertion never happened? Let's assert 0. Yeah, this assertion failed. And will it fail in release? You see, also, in release it also happens. But here it did not happen. Let's also look at this. Okay, 0, 1, 0, 1, 1, 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 5, 3, 0, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3, 7, 3, 8, and 3, 9. 4, 0, 4, 1, 4, 2, 4, 3 is interesting. What is this? Why is... Ah, 4, 3 just it took one triple. 4, 4. 4, 4. Ah, 4, 5 might be interesting. So 4, 5. Okay, let's jump to 4, 4, 14. So this is 6. This is 7. This is 8. This is 9. This is 10. This is 11. This is 13. Ah, this is 12. This is 13. This is 14. Just 14. This is 14. Okay, this seems like 15. Ah, looks or seems? Both. Both. 15. 16. Ah. Okay. Actually, let's just submit. I believe we did everything as careful as possible. Not great, not terrible. Only not terrible, but maybe great. Astounding. We did it. Thank you for watching.